All right, let's get going here. So I have the next test, and I know I'm giving you an extension on the other one with a 10-point penalty, but I want to at least have this up here for people who would want it. So unfortunately, when I printed it, it didn't do double-sided. So what I'm going to do is pass around the first page, and then I'll pass around the second page. So this will be up through 10-8. So I have it due on the 17th, which is a week from, no, 5 days. Uh-oh. No, let's not make it due Monday. Let's make it due this Friday instead. I'm just kidding with you. Let's just say it's 4 problems. A week. So ignore the due date on here. 1 week. So go ahead and just take one of each and pass it around. What's coming around right now is due a week from today. It says on it the due on the 17th, but it's due on the 19th. So how do y'all feel about this so far? I mean, I've had some feedback on things here. Are you feeling overwhelmed? Here you go. Are you feeling overwhelmed or yeah? Yeah. Oh, extras? Okay. There's 2 pages to that. I'll send that document, the test, the mini exam 3. I'll send it out again electronically. I still have students who have not picked up their exams. And quite frankly, I don't want to have them in my pile of stuff anymore. So I'm just going to call your name. I've invited you to come talk to me about your grade. If you haven't done that, then, you know, that's your prerogative. Jason? Cameron? Mm-hmm. Is that you? Sorry, I just can't. It's a nice signature. I just can't read it. Xavier? Garrett? You called me yesterday? You texted me or something, then all of a sudden, was that an accident? No. I texted you back. Did you get it? Oh, the phone randomly died. Oh, okay. All right. Okay. Okay. Nathan? All right, so everyone has their exam 2 turned in? All right, we left off last time, we were talking about vector functions, right? Space curves. And we got as far as the end of 10.7, right? We integrated. Unfortunately, my video did not get that last integration I did, but I didn't bother to fix it because at least the video is saved. Remember, my computer died right there in the middle of class, so at least the video was there still. So that's where we finished last time, and now we're going to pick up in 11.8, and this will be the last section in Chapter 10. That's good news for us, right? We're ready to move on to a different chapter. I think 10.8. Yes, I did mean 10.8. Getting old? Oh, yeah. It's fun. Okay, 10.8. Arc length and curvature. Now, a couple of instructors that teach Cal 3, there's actually only like 3 of us here that 3 or 4 that actually do it, you know, on a normal basis. A lot of us have decided to take this section out, but I think it's so short and to the point that we can knock it out pretty quick. It's just a couple of formulas, and it's kind of cool to have this, you know, in our bag of tricks. So 10.8, arc length and curvature. Remember that when we have a vector function, it's moving through 2 or 3 dimensional space, right? That if it's in 2-dimensional space, tracing out some curve in the plane, then we should be able to somehow take that curve off the sheet of paper, stretch it out, and rectify some sort of length for it, right? And that's what this allows us to do. And it also gives us some meaning to an integral. If we take the curve and we want to measure its length, the arc length from A to B, so we'd have to have some restrictions on our variable t. Remember, t gives us time starting and ending, draws the curve. If we start at A and end at B with our time, then this integral will give us the arc length. And so it's the integral A to B of the magnitude of the derivative of the vector function, which is just the magnitude. Remember, magnitude is square root of the sum of the components squared. So f prime of t squared and g prime of t are just the derivatives back up here of that f and g components, those component functions. Just take their derivatives, square them, take square root, integrate that, and we're in business. We'll get the arc length. All right? So here's the first example. Find the arc length of r of t is cosine t sine t. What is that curve? What is that? Circle. Radius? 1. Right? T goes from 0 to 2 pi. So this just draws one circle. So what should the arc length be? What's the circumference of a circle? 2 pi r. And if the radius here is 1, our answer should then be 2 pi. Let's see if the formula gives us 2 pi. All right, here it comes. So first thing I need to do is I'm going to find the derivative. The derivative is negative sine t, cosine t. You might imagine that on one of your mini exam take-homes, the derivative would probably be a little bit more challenging than that, right? But this gives us the basic idea. Now we want the magnitude, right? The magnitude is square root of negative sine squared is just sine squared t. I mean, negative sine squared t, when you square it, the negative goes away, right? So we don't care about it. Plus the g component, the derivative of g, which was the cosine t squared, which is just what? 1. So my integral then becomes integral from a to b, so 0 to 2 pi, of the magnitude of the derivative, which in this case was 1, dt. T is we're integrating with respect to the variable t. So what's the antiderivative of 1? It's just t in this case, and evaluated from 0 to 2 pi. You plug in 2 pi, you get 2 pi, right? Have you all seen that notation before? Okay, integrate t, or integrate 1, we get t. We're going to go from 0 to 2 pi. Plug in 2 pi first, right? You get 2 pi. Subtract, plug in 0, you get 0. Answer's 2 pi. That matches what we would think we would get, right? Circumference of circle. This is, well, that's a great question. There is a difference. The difference between a parametric and vector is that a vector function spits out vectors. The parametric will spit out a point. But we're seeing that it's pretty much the same thing. The vector points to a point, and that point corresponds to something on the curve. So they draw the same thing, but one of them spits out vectors, the other one's points. All right. Next thing. Am I going to still do my little screen captures here? I guess so. I've been looking at upgrading my computer, but I just can't justify it yet. I want to do the i7 processor. I have an i5, but it's working, right? It seems to be working, so I can't really justify like $2,500 just for a little process. Well, that's the thing. This kind of does, man. I've got a lot of different applications running at one time. So. Yeah. Okay. Next one. Oh, whoa. Here's my curve here. So I could have picked any interval zero. I went 0 to 2 pi, so obviously that just gives you the red is the circumference. Now, if we go to 3D, right? Vector function, three-dimensional, same process. The only thing that changes is in our formula here, right? Our integral goes from A to B. The only thing you do is you throw in that z component, the h vector function, derivative, square it, add it in there. You're off to the races. All right. So find the arc length here. So what's my derivative? Pretty much the same thing we just had, right? Except now we've got a 1 there. So the magnitude of the derivative will be square root of sine squared t plus cosine squared t, which we already know is 1, plus 1. So this is just root 2. And then if we integrate that, oh, hold on now. Now we got an issue. Because I'm not giving you A and B, am I? But I'm telling you where we start from and where we end at. So in other words, at some value of t, right, at t is A, which I don't know what A is, we should be at the starting point, 1, 0, 0. And when t is B, we should be at some ending point, negative 1, 0 pi. This is going to come up in your take-home test, obviously. I'm not going to give you, oh, here's just t. You're going to have to recover t from the starting and ending point. But sometimes it's pretty easy to see it. What are we going to be looking at to figure out this point? Are we looking at the derivative, or are we looking at the original vector function? The original vector function. Can you see what A would be? 0. Why? Well, I don't think that's much of a challenge, right? T is the z component, right? So whatever that last z component is what t is. So at the first point up there, that 0, that is going to be my, that's going to be my A. And then over here, pi. Does it work though? Plug 0 into R of t. What do you get? Plug 0 in there for t. You get 1, 0, 0, right? So it matches up with the point. What happens if you plug pi into R of t? Cosine of pi, negative 1. Sine of pi, 0. And then pi. I don't anticipate that your take-home test has a vector function that easy to recover. Let me see. Do I even have an arc length problem on here? Oh, I do. Something like it. Number 3. I'll give you a little hint on number 3 while we're sitting here. I give you a vector function. I say it represents the position of a particle at time. And then I tell you that the particle starts, that's supposed to say starts, not startes, starts at he point, the point. I have all sorts of grammatical errors in this thing. I don't care. If the particle starts at the point 0, 0, 0 and moves a distance of 4 units along the curve, then where is it now? I'll just give you the hint that this is related to arc length. I've told you how far it's moved, and you have to figure out what the other end, where it stops. So you'll just play with it and see what happens. All right, so I'm going to integrate here from where to where? 0 to pi. And I'm integrating the constant root 2 dt. So this is just root 2t and 0 to 2 pi. That's just going to be 2 root 2, just pi. Thank you. And that's just going to be, what is that going to be? Yeah. So you'll just have pi root 2. There we go. Or 2 root 2 pi, however you want to put it. But that's it. This is the actual curve that we just found the arc length of. It was cosine t sine t, so it draws circles, but the z component is a linear thing, so it's going up as it draws. So it's like a little spring or spiral-ish time thing. And we said, okay, let t go from 0 to pi. Well, that's 2 pi. Oops, we only wanted to go to pi, so right around in here somewhere. We found the length of that red arc. So here's another one. Find the arc length of this one. And that's kind of a nasty looking Rft. There's the picture of it, but I'm going to take the picture out of here. Well, I'm going to try and take the picture out of here so that I can write on this page. So let's get a derivative here. Derivative of this is 3t to the 1/2, which is the same as square root of t. Derivative cosine 2t is negative 2 sine 2t. Derivative of sine 2t is 2 cosine 2t. And then if we want to try and get the magnitude of that derivative, then we take the square root of each thing squared. So 9t plus 4 sine squared 2t plus, yeah, the 2's inside, it's the argument. And then what, 4 cosine squared 2t? The negative goes away because we square it. So over here we get square root 9t plus 4. How did I get 4? Well, I'll go one more step. Yeah. I factored out a 4 from the sine and cosine terms. Right? Factor out a 4 out of these two terms. Pull it out, and then sine squared 2t plus cosine squared 2t is, careful, 1. Sine squared of junk plus sine squared or cosine squared of junk, same exact junk, doesn't matter what's there, that's 1. So now that'll be 1 times 4, so we'll get 4 there. So square root 9t plus 4. Well, if what's under there turns out to be a perfect square, then possibly not, you know. But a lot of times, just like arc length in Cal 1 or 2, in Cal 2, arc length in Cal 2 a lot of times turned out to be square roots. And the integrals could be somewhat challenging because of that. Please sign in, pass it around. All right, so our integral is going to go from 0 to 1. That was given, right? Square root 9t plus 4 dt. And you would integrate that, just pretty much basic substitution there. So dot, dot, dot. I'll let you finish that. Okay, curvature. This is kind of interesting. The curvature of a vector function is a number which represents how quickly a curve is changing direction at any given point. The curvature can be found by computing one of the following two formulas. So this k here is equal to k for curvature, not c. C we use for constant, so they use k. Curvature is the magnitude. What's capital T prime? The tangent vector, but not just the tangent, it's something else. It's the unit tangent. Okay, unit tangent divided by the magnitude of the derivative vector. So that's one way you can compute it. Or you can compute this, which is the derivative of the vector function crossed with its second derivative over the derivative, the magnitude of the first derivative cubed. And I put here, this is only good when we're in R3. Why? Because it's a cross product. You can only do cross products in R3. Kind of. I wanted to talk to you all about that real quick, because I think it comes up at some point this semester. I mean, as like a take-home test or something. I remember this. Can you cross, let's say I took this vector and I asked you to cross these. Could you cross those? Yeah, I mean, technically they're in two-dimensional space, so we don't have an idea of cross product. But if you just extend this out, you know, right now those are two vectors in 2D, right? Flat piece of paper, two vectors. But if you now say, look, just lay that on the ground and imagine it's really in three-dimensional space, then you could convert these vectors over to these vectors, right? Just always using 0 for the z component. And now the cross product is defined. So there are ways to get around it, kind of. But we usually say, I mean, we've actually changed it, though. I mean, we've changed a vector that was two-dimensional to a vector that's three-dimensional. Yes? Well, it would always point out in the direction of the z-axis. Yeah. Exactly. That's what I'm saying. But the thing is, you could still do it. You could still mechanically do it. The concept of a two-dimensional vector, you could really look at it as, wait a minute, no, it's actually in 3D, but laying on the ground. All right. Now, you may look at these two formulas and you'd be like, hey, you know, like, why would I ever use that? That looks more complicated. But it turns out sometimes this is easier to compute than the one up there. So it just depends on the problem. Let's go ahead and take a look at one. The example below shows that the curvature of a circle is constant. Oh, and I didn't even talk about curvature. But imagine like a roller coaster, right? Is the idea of a three-dimensional vector function, right? Just imagine you're moving on a roller coaster in three-dimensional space. You're following a path, right? The curvature is, you know, what you would think it would be is how fast, at every point, how fast are you turning? So if your direction is a vector, how long it is, how fast you're going, then you want to know like how quickly that vector is changing direction. That's curvature. Make sense? On a circle, that should be the same no matter what, right? It's always curving the same. There's the tangent vector, right? And as I go around, it's constant. How quickly it's turning. I think sometimes it's easier if I actually animate this and let it play itself at a constant speed. So as I'm moving, my curvature is constant. And the computation is 1. The example below shows a vector function with a curvature which is not constant. So this one's kind of cool. Notice right now how big is, what's the computation of the curvature right now? Right here at the origin. At t equals 0, look at the curvature. 333,331. A lot of curvature. That means as I start off, it's really wanting to turn. But as time goes on, let's see what happens. Lots of curvature, and now what's happening to the curvature? Look at it. It's dropping down. Now it's big. I think maybe I need to slow this down just a little bit. There we go. See, it's like a spiral, right? In the very beginning, it's very tight spiral. So as I'm moving out, it's really turning, right? But as I get wider, I don't have to turn as fast. Do y'all see that? I don't know what. Well, I think I actually put what the function is. It's not the golden ratio. It's not the golden spiral. It's that, I think. I think that's what it was. I don't know. Well, that doesn't look like it. Do you really want to know what that was? It was basically t cubed cosine 10t, t cubed sine 10t. So what was happening is it was drawing cosine and sine draw a circle, but I'm changing its amplitude by the x cubed in front. And then inside, I'm changing the period with the 10s. So I'm doing lots of things to make that thing spiral away. Format. Next note. Find the curvature. So we're going to have to compute the curvature, and I have 2 options, right? 2 options. In one of them, I have to have the derivative of the unit tangent vector divided by the derivative of the vector function itself, and then magnitudes, or right? Excuse me. Or we could have the other formula, right? Which one do you want to do? Do you have a preference? Do you care, formula 1 or 2? Do you want to try them both and see what happens? Or like try one, and if it sucks, go to the other one? Okay, let's try the first one. Magnitude capital T prime T over magnitude R prime T. All right, let's find R prime. R prime is there, got it. 1, 1, 2t. The magnitude of that is square root of 1 plus 1 plus 4t squared, so 2 plus 4t squared. The sum of the square of the components. What was capital T of t? Yeah, look back from last class. We did this. Well, that's the derivative of the unit tangent vector up there, though. Yeah, it's the derivative. Y'all see that? That's what makes this formula suck sometimes. Because what's the What's capital T? What's capital T of T? Back on note 10.7.10 is where that comes from. It's the derivative over its own magnitude, right? It's the derivative over its own magnitude. So this is 1 square root 2 plus 4t squared, 1 over square root 2 plus 4t squared, and then 2t over square root 2 plus 4t squared. Do y'all follow me there? The derivative, capital T, by definition, is r prime of t over its own derivative, which means scale r prime by its own length. So that's this. But in my formula, it sucks because I need the derivative, right, of t? And the derivative of this is the derivative of each of the components. And you've got square roots in there. And it's not like we can't take the derivative, but it just doesn't look appealing to me, right? Does it look appealing to you? Maybe we could do it, but at this point I'm starting to go, I don't know about this, you know? Because not only will I have to take the derivative, I'm then going to have to find its magnitude. And then divide it by the magnitude of r. So it's starting to really, like, I'm starting to feel like maybe the other formula might be better. Shall we see? So I'm going to go, well, first I'm going to switch back to a pen. And I'm going to say, yeah, that's a weird looking M. Try it again. So I go for formula 2 instead. Now formula 2 is a cross product and all that. So that looked a little intimidating also. But I'll go for it. So I think I'll just copy this real quick and I'll clear this out. So the other definition for K was K is magnitude r prime t crossed with r double prime, right? We haven't used that before. T all over the magnitude of r, the derivative again, cubed. So all we really need is the first and second derivatives, right? Okay. First derivative, we already got it. 112t. Oh man, and look at its derivative. The derivative, second derivative, would be 0, 0, 2. And now I need to cross these two together. Now, the cross product, on most of your calculators, cross products will not take variables as input, unless you run into the TI-89 or some of the ones that we wrote the programs in might accept it. But do you see how one of the components is 2t? So, so can you do this by hand? Let's see. Someone try and cross this with using 2t as a variable in theirs and see if it works. What did you get? 2 minus, so 2, negative 2, and 0? 2, negative 2, and 0? So it's taking the t in? Okay, do me a favor. Just type, go to a clean screen, just type t. Hit enter. What do you get? 2? Let's try this. I know some of you like this way of crossing. 1, 1, 2t. Since I never showed this, I'll do it here. How do you find the cross product using this method? So this is the one where you write down ijk, then you write down the first vector, second vector. If you want to know what I is, you cover up the I column, and then you find the determinant over here. So what's the determinant on these? So how do you do that? 1 times 2 is 2, and then subtract this times this. So I get 2 minus nothing, so 2. That's the I component. Now I get the J component. To do J, I cover up the J, and I do determinant on those 4. So that's what? 2 and 0, but you don't put that number there, you put the negative of that, or opposite sign. So -2 goes here. It's always like that for J. You do the opposite sign of what you get when you do determinant. And then to get, what? Like that, something like that, if it helps you remember. Okay. Okay, for K, cover this up. What do you get there? 0. So yes, it did. Does that only work? I don't know how the algorithm in the computer is doing it, to tell you the truth. I mean, one way you could check it is to just put like the vector t, 2t, 3t, and try and cross it with like, 5, -2, 7, something like that, and see what it spits out. I know the 89s will do it. Looks like it's doing okay. The only problem you would ever run into is if t was already given a value before you started running that routine. So like you can go in and define t to be a number right now in your calculator. So if you define t to be 2, then it's going to go in there and replace all your t's with 2's, which wouldn't have changed our answer, would it have? Yeah, because everything gets killed off. So it still may not work on your calculator. I don't know yet. Yeah, but t isn't 0 necessarily. What is this? Get out of here. Just postponed. Been postponing for about 4 or 5 days now. All right, let's get to this. Come on, I want to get out of this section real bad. So that is the cross product, isn't it? This is r prime t crossed with r double prime t. And so what we need is its magnitude. So what's the magnitude of that? Square root of 8? Root 8. So that, my friends, are we there yet? No, we're not there yet. I'm saying friends, we're not there yet. That, everybody, is just the numerator, right? Now you need the denominator. Y'all? Y'all ready? Okay, the derivative, right, is that up there? We need its magnitude. What's the magnitude of the derivative? I think we may have found that in the last problem, didn't we? No? What's the magnitude of the derivative? Square root of, didn't we do this? 2 plus 4t squared? And if we cube it, then we just, raise it to the 3rd power. I know I'm kind of all over the place, but that's this. I think I'm ready to put a final answer here. So K is 8. Was it 8? Root 8. Root 8 over root 2 plus 4t squared cubed. Sure. And of course, you could clean that up and do stuff with it, but I'm at a point now where if someone gives me a t, I can give you a curvature, right? That was much cleaner than the other one. Yes? No? Were you saying something? Okay. Do y'all agree that one worked out a lot nicer than the other one would have potentially? All right. So you got to kind of know when to use which formula, and usually you quit when one of them looks too much. You try the other one. I think we're done with this section. There's the homework. And we move on. Oh, by the way, I've almost, well, Remember I gave you all that handout for all the problems from 10.5? I did post the solutions to those yesterday. It took me a little while. I just kind of put it on the back burner and kept it there for a long time, and finally got a little bit of a nudge from one of your classmates to get it done, so I did. But I don't have 10.6 or 10.7 or 10.8 up. And I'll just make that part of my homework for the next couple of days. Okay? So slowly be getting those out there. All right, we are done with chapter 10. Yay. Chapter 11. Now we truly get to test whether or not I need the i7 processor or not. Because we got some pretty complicated visual stuff going to happen today. I've done my bench test on this. You know, I've done this. I've run this at home. I've projected from here to my TV, and everything works beautifully. We'll see if it happens here. All right. Everyone have their notes? Okay. Functions of several variables. So pretty much everything that you've done, I think this is what I say, don't I? Everything we've seen up to this point in our Cal 1 and most of Cal 2, it was calculus of a single real variable, meaning that every function we looked at, one input, one output, one input, one output. Now we start to look at the idea of having a function of several variables. So you have maybe 2 inputs and 1 output, or 3 inputs and 1 output, or 4 inputs and 1 output. Or you could have 2 inputs, 2 outputs, 3 inputs, 2 outputs, 4 inputs, 4 outputs, 5 inputs, 7 outputs. It doesn't matter. You can have more outputs than inputs. It doesn't matter. All that has to happen is that for every input, we assign values to however many outputs we have. I'll give you an example. Well, no, I won't give you an example. But you can have, what we say is this. Let's say you have a function that's this, f of x equals y. Well, what goes in here? X. What comes out? Y, right? One input, one output. The input, x, is a number usually that comes off of the number line. So what we say is that this function goes from r, and it spits out a number where? R. A number to a number. So mathematically speaking, for those people doing like more math, we would say this is a function that goes from R1 into R1. So R into R. Function that takes a number, spits out a number. But I could have a function that goes from any dimensional space, Rn, into any other dimensional space, Rm, where n and m don't have to be equal. And n doesn't have to be bigger than m. They just have to be non-negative integers. We don't really have the idea of negative space. What we're going to look at right now is what happens when we have a function of 2 variables, f of x, y. So you give me 2 inputs, and then I will provide, from those 2 inputs, I will provide you with a single output. I'm going to do something with those numbers that you give me, do some computation, and I'm going to spit out a value z. So what we would have in this case is a function that goes from what? If I give it 2 things, right? Then it comes from 2-dimensional space, R2, and it goes to where? R1. But I say here, note also that to be a function, there still exists the need to have 1 input and 1 output. The input, though, here, the input is an ordered pair. So your input is no longer a single number. It's an ordered pair, x, y. In ordered meaning, x, y is different than y, x. So I'm going to be plugging an ordered pair into a function. It's going to spit out a number on a number line. That's what's happening. Okay? Ooh. With this notation, it's important to see that the domain is, like I said, ordered pairs. That means our domain is in R2, two-dimensional space, and our range is R. It's going to be a number. How many dimensions is that total? 2 for the input, 1 for the output, right? 3 dimensions total. So to be able to visualize this function and see what's happening, we need 3 dimensions, which is freaking fantastic, right? Because we live in 3D. We can visualize 3D. So let's just try some quick stuff here with this function. And then we'll start taking looks at what these things look like. Part A. All right, find f of 2, 1. That just means plug in 2 for what and 1 for what? 2 for x, 1 for y. Go ahead. What do you get? What is it? -2. Part B. Zero, 0. A is -1. Hold on. Let's do B real quick. B is 0 plus 1, 1. Square root of 1 is 1 over -3, so -1/3. Now let's go back to A. Is A all right? 2 plus 1 plus 1 is 4. Root 4 is 2 on the bottom. Plugging in 2, it's -1. Yeah, -2. Next one, -4, 1. What do you get there? Oh, you get a negative under the radical, don't you? So for part C, we're going to have undefined. I know this class is Cal 3, but it's not complex variables. Complex variables is where you start to actually deal with I. So you have to go through a little more math before we deal with I. And there's a reason why, and I'll explain it to you. I'll try to the best I can. This is my most basic explanation as to why we don't study complex variables in I right now. The reason is because to visualize a complex number, you need 2 dimensions to visualize what it is. And then if you have a function that you're going to that you're going to plug that complex number into, it's going to spit out another complex number. You're going to need 2 dimensions for its output, which means that you need 4 dimensions to visualize a complex valued function. And the wheels come off after we get out of 3 dimensions because you can't visualize it anymore. So we wait till pretty far into your math life before we say, start thinking in 4 dimensions. Does that make sense? So we avoid it until later. Yeah. It's like everything you thought you knew isn't what you thought you knew. No. I mean, it is. It is pretty much that way because what winds up happening is that you come to realize that your real numbers are just one axis of the complex plane, which is actually 2-dimensional, and all your real numbers are actually living inside of a bigger space of numbers. And so all the math that you do in real numbers can actually be looked at as complex valued, so you can basically put on your complex valued super goggles and do every integral you've ever done, everything else with complex valued functions in mind, and it can make life extremely easy if you look at it through the complex variables instead of being stuck on the real number line. That's, well, it's a number times 0i, or number plus 0i. Okay, I could go off all day on complex numbers. I don't want to, because I could. Okay, so we say it's undefined. At this point, we're kind of stuck, and we just have to accept that. All right, now determine the domain and sketch the domain. So we said the domain is what we can and can't plug in, right? The domain comes from 2-dimensional space. So I need to figure out what I can and cannot plug into this function. I already know I can't plug in -4, 1. But I don't think -4, 2 would work either, right? How about -4, 0? Wouldn't work either, right? There's a whole bunch of stuff I can't plug in. Yeah, there's a lot, but watch this. I need to be more efficient than that. For part D, I need to make sure, well, you might have said it. I need to make sure what's underneath that radical, oops, x plus y plus 1, I need to assure myself that that's greater than or equal to 0, don't I? What's underneath the radical sign up there in the numerator has to be a positive or non-negative number. And if I solve that inequality by moving things around, negative x minus 1, God, what's going on with this thing? It wants me to keep talking about complex numbers. It's like, you were on the right path. So what is that? Y greater than or equal? I'm doing this in my 0302 class this semester. It's a linear inequality in two variables. It's a shaded part of the plane. It's a line and then shaded one side or the other. Right? If that was y equals negative x minus 1, it would be y equals mx plus b. Okay? The greater than or equal, all it does is makes a shade one side or the other. Now, that's not the only restriction I have. I have something else that I have to consider here. I also have to consider the fact that I can't be 3, right? X can't be 3. Because if x is 3, then I have division by 0. But what is x equals 3 in two-dimensional space? X equals 3 is a point on a number line in R1, but we're in R2 now, right? Domain is R2. X equals 3 in R2 is a vertical line through x equals 3. Okay, so let's see if we can't get this all together here. I'm going to draw a picture. My domain's going to be a picture. And so will yours on a test. All right, first thing I'm going to do is I'm going to draw that linear inequality. Y is greater than or equal to negative x minus 1. So negative x minus 1 has a y-intercept of negative 1, has a slope of negative 1, so it's going to go like kind of down, left to right, it's going to go down. I'll pick a nice color here. Oh, is it going to be a solid line or a dashed line? Do I want to include the line or not? Yes, I do want to include it because the inequality has the equals on it. If it was not, then I would make it dashed. Now, which side of the line do I shade? How can you check or how can you figure it out? Just plug in a test point. Just take any point you want that doesn't lie on the line, plug it into the original inequality, see if it's true or false. I always like to take the origin if it's available. The origin is the point 0, 0. Plug 0, 0 into that inequality. Is it true or false? It's true, right? Plug 0, 0 right in here, and you get 1 is greater than or equal to 0. That's true, which means that the origin is part of the solution set, which means everything on that side of the line is part of the solution set. So far I have everything over here like this, right? Except 3. So I have to somehow come in here and say, no 3. So here's, let's say 1, here's 2, here's 3. How do I say except 3? See, it's kind of hard to do that, right? So I'm just going to put a dashed line through 3 to let you know that 3 is not there, that you can't plug in 3. So your domain is anything that lives on this line, anything above that shaded region, except was it 3 or negative 3? It was 3. Except 3, we cannot have 3, so anything that lies on the line 3 is not in there. Take it out. Now, determining the range is much more challenging. Range is always harder with functions. So let's just try it. Let's just try it. Can you get 0 out of this function? Can 0 come out? Is there any way you can get 0 to come out of here? What if you choose negative 1 for x, 0 for y? Can you get it to, would that be 0? Negative 1 for x, 0 for y. It would work, wouldn't it? You get 0 on top? Well, yes, because that's the inequality right there when it's 0. Anything on that line. So we can get 0 to come out, right? 0 can come out. Can we get every positive number to come out? No? what if I help you with this? What if I let y be 0? Wouldn't we have this? Wouldn't we have that? If y was 0, isn't that what we have? Can I pick x's here that will spit out every negative number? I'd have to make these change, right? This change, but I'm restricted. I can only go so far with this, right? Or else I start getting negatives underneath here. Do you see the challenge in range? It's difficult to narrow down just by looking at something what's coming out. You actually could do something like we did in like college algebra class. You could try and find its inverse function and then find its domain. The problem here is that we have 2 coming in and 1 coming out, so inverse isn't what it used to be. All right, I got to sneeze. So for range, I'm going to just leave range, okay? And on the homework and stuff, I leave it as an optional thing for range. I'll show you how we're going to get range in a second. We're going to do it geometrically with the graph. It's kind of cheating, but it's all right. Okay. Now, let's see if I can break my computer. If we choose points in R2 and we plug them into a function, so we start plugging these values in, right? Start plugging in. Some of them may work, some of them may not. Some are in domain, some of them aren't. We start plugging them in. Then we get a bunch of points and we begin to see the outputs. So here we go. Here is the ground here is my domain. For every point on the ground, I plug in a point and it spits out something and it has a height to it. Okay? For every x, y, there's a z that comes out. So if I plug in a few points, you know, for each point there's something, I go up and graph it, and that's the height. If I start doing more and more and more, and more and more and more, and more and more and more, and more and more and more, I start to construct a surface, right? A 3-dimensional surface. So that is what a function f of xy, z equals f of xy, looks like. It's a surface in 3-dimensional space. Got it? The input being the ground and the output being the z-axis. Now I'm going to take this out of here so that I don't make my computer freak out too much. And I have another way of demonstrating this. This is kind of cool. On the left is just the domain. So I said, remember, you can pick any point you want over here. As long as it's a domain, you plug it in. So I'm just picking values over here in the domain, an x and a y. And then over here, 3-dimensionally, that's my input on the ground, and it's going to some z, and that's making my surface above it, right? So this is just that on the ground is my domain. If I look at it from the top, right, that's me getting up above it and just looking straight down. I have my surface, and below it is my domain, which maps every point up to something on the surface. See it or not? Yeah? There we go. Well, if I move, all I'm going to be is a different point somewhere on the graph. That's all it's going to be. Oh, okay. No, I understand what you're saying. If I extend this out, then that would start, the surface would keep going out. Yes. This surface keeps going. Well, it's only defined over the domain, though. You know? It may have been. When there, yeah, notice when I drag, this whole shape becomes a little weird. When I let go, it re-renders. That's the way Mathematica does it. You can't do that in Wolfram Alpha. It doesn't allow you to do that sort of dynamic updating. Yeah, it's pretty complicated. Sometimes you can do it and it won't change the shape, but other times it has to re-render it. You'll see that a lot now from here on out. I made it up. I don't know what it is. Actually, looks like it has some sine stuff in it. Sine, cosine stuff. Well, you know, I'm moving on. Okay, so check this out. Isn't that the problem we just did? That's the problem we just did where I asked you, okay, this, and I said find the domain. Check it out. Here it is. This is the actual surface. If you were to plug points in, here's what you would get. Okay, that's the surface. Now, what's really cool is if we look at it from the top, like I said, that means we're going to look at it and we're going to kind of look down transparently through down to the domain. It should look exactly like we had earlier. Didn't we say it was that line, everything shaded above, except take out x is 3? That's the domain right there. It's just looking down from the top. Now, something is happening weird at 3. Can you see? It's asymptotic. If I turn it like this, that's actually that's the angle we should be looking at it from. Right, there's our line, there's x is 3, and what's happening is that surface, as you go to it, it's doing this thing. It's asymptotic. So can we determine a range from here? It looks like because it's asymptotic, it should go up to infinity, right? Should go down to negative infinity. We did have 0. I just wonder if we have everything in between. You know, can you achieve every number in between? Looks like it, but we would have to verify it algebraically. All right, let's look at another one. If f of x, y equals x natural log y squared minus x, then find f of 3, 2. What's f of 3, 2? F of 3, 2 is plugging in 3 for x, get 3 natural log of y, which is 2 squared minus 3. So it equals 3 natural log of 1. Natural log of 1 is 0. Right? So you get 0. That's just a little practice of plugging in. Determine the domain. Well, in the last problem, we had a square root, so we couldn't have negative under square root. Here we have a natural log. What's the restriction on natural log functions? You can't have, whatever's inside the log cannot be what? 0 or negative. So strictly positive, right? Strictly positive. So for part B, what I need the part inside of the natural log, what do we call the thing that's inside the function? Call it the argument. The argument of the natural log is y squared minus x. We need that to be strictly greater than 0. Can't be 0, can't be negative. The natural log of 0 is undefined. Natural log of negative number is undefined. That, y'all, is an inequality again, but it's nonlinear. This is a quadratic inequality. Quadratic inequalities do not work out like linear inequalities work out. They're a little more complicated. But if I change this if I switch it to this, what is that geometrically in two-dimensional space? It's a parabola. Opens up sideways like this, right? So if I'm looking at this, I can draw my parabola sideways. Now, do I want to include the parabola itself? No, because, again, it was, not again, because this one does not have the equal sign. It is a strictly greater than, y squared strictly greater than x. So I'm going to draw my parabola sideways like this. And what I know is that the region that I should be shading here is either inside this parabola or outside this parabola. So again, I can pick a test point, and I can't pick the origin, right? I can't pick 0, 0. So I'll pick something over here like negative 1, 0. Let me test that. You plug in negative 1 for x. I'm going to test it in here. Negative 1 for x. And plug in 0 for y. Is that true? Is 0 squared greater than negative 1? Yes. That means that point works. That means everything on that side of the parabola should work. So it should be everything out here. Okay? Everything outside that parabola and not including the boundary. The range, we'll save it. Well, the problem becomes trying to figure out what's happening. Like, if you can determine, yes, I can make it go to infinity, I can make it go to a negative infinity. It's can you achieve everything in between, though? That's the issue. Here it is. Here is that function, that surface graphed. It's almost like it almost looks like a plane, but you had some catastrophic like sinkhole that just like totally destroyed the plane, right? If I look at it from the top, there's our parabola that's cutting out our domain. That's pretty cool, right? Now, the computer, just so you know, when you see these jagged edges, that's the computer's way of saying, like, shit, you know, I'm like at the edge of what I can do. Now, the computer will do more, okay? The computer will do more. There's set pre-tolerances that I can adjust. So if I want it to be a better picture, I can tell it to compute more points and it will make it better. But then you have to give up other things like the speed at which it will re-render the picture. If I have this thing go and do a lot of points, it may take 3 or 4 minutes for it to re-render the picture. So it's always going the most optimum for viewing and us just getting the idea, okay? Determine the domain and sketch the domain in R2. Determine the range. Well, we have a square root again, don't we? And we know that for square roots, we must provide that the radicand is never negative, right? So I need 9 minus x squared minus y squared to be greater than or equal to 0, right? This again is a quadratic inequality. But if we just notice that if I move the x squared and y squared over, if that wasn't an inequality, if it was just equality, it would be a what? A circle radius 3. So this is just either inside the circle or outside the circle. I think it's obvious to see, right? Just test a point, 0, 0 works. So it's inside the circle. So my domain, and it's including the boundary, right? Because you can be 0. So it includes the boundary. So it's everything inside. So it's a solid, or a disk, radius 3. Circle and everything in it, radius 3. Range, again, Well, the range might actually be achievable on this one. Yeah, you can't, you cannot get anything bigger than the square root of 9, right? Because you're subtracting x squared. X squared is guaranteed to be positive, right? Y squared is guaranteed to be positive. So if you subtract x squared and you subtract y squared, then you're always going to be taking something away from 9, except if they're both 0. So the biggest this would ever get would be square root of 9, which is 3. The smallest it could ever be would be 0, because this cannot be negative, can it? You can never take the square root of something and get a negative number. So it seems reasonable to think it's everything between, what, 0 and 3? Reasonable. Let's see here. That's it. There it is. It's the top half of the sphere, right? That's what that function was. It looks like the top half of the sphere. That's right. We'd have to have plus or minus. See, now we have this idea of function, so you do have to pass almost like a vertical line test. If you try and pass a line straight down through this, if you punch the top of the surface, then there can't be another side that gets punched. Because that would mean that 2 points on the plane in your domain go to 2 different places, and that violates a function. There's ways around that, just not yet, like not in this class. Oh, okay, so what if we have a function of 3 variables then? So instead of you giving me x, y, and me giving you a z, you give me x, y, z, and I give you a, I don't know, whatever, w. The problem is that we're going to run into is that the input, right, requires 3 dimensions. The output requires 1 dimension. And therefore, to visualize, we need 4. But that's not happening. Some of the most brilliant mathematicians are blind and have been blind their whole lives. And it's because they're not fixed in 3-dimensional space the way we are. They can think 4 dimensions, 5th dimension a lot easier than we can. I'm just saying some of them. You know what I'm saying? So, so that's not happening. I should say that's not happening easily for us because 4 dimensions isn't that hard to visualize, right? I mean, we live in actual 4-dimensional space, physical space, 3 dimensions, and then time being the 4th, right? So like I'm physically at this point right here at this time, that's 3-dimensional, but you take the time into account, that's the 4th variable running in the background. Now I'm over here, so what's changed? Well, my position and time has changed. Now I'm back here, I'm in the same position, but time has changed. So, you know, there's actually 4 dimensions always happening for us, but it's just more difficult to visualize it. But we can still talk about its domain, because its domain is in 3 space, isn't it? So now look at that function. F of x, y, z equals square root of 9 minus x squared minus y squared minus z squared. So first plug in, 1, 2, 0. And what do you get? Who cares, right? Just plug in numbers, right? But determine the domain. Oh, we're going to do part A, okay? I know. You have to guess which one I'm doing. A, we're going to do the second A. What's the domain of this thing? What's the domain? We need 9 minus x squared minus y squared minus z squared to be greater than or equal to 0. Are you kidding me? We can move those over like that. And that is a what? That is a sphere, radius 3, but we're including everything inside of it, so it's actually a solid ball, radius 3. It's a quadratic surface, isn't it? If I make that an equation, that's a quadratic surface. So the domain of this is a quadratic surface, specifically a solid ball. The domain doesn't matter because, see, like in 2 space, I pick a point, right? That point has to go in and go to exactly one place. When you take a point and you plug it into that, we had the top half of the sphere, it spit it out, it went to the top half. If we would have done negative root, it would have gone to the bottom. So then from that point, you would go to 2 places, right? 1 point in, 2 places out. Here, a point is anywhere in this ball, right? So I pick something up here, plug it in, that goes somewhere. If I pick a point on the bottom, that's no longer this point on top. Like they're not connected to each other anymore. These are completely separate points in 3-dimensional space. Does that make sense? Yeah, I mean, it's hard to tell where it's going, but we can tell where it's coming from, right? So I think I might, here's kind of what's happening. We take something in R3, it goes to R, right? That's what's happening with this function. 3 in, 1 out. if you want a picture of the domain, the domain is three-dimensional. Here's three-dimensional space. Something in there, X, Y, Z. I pick something out of here, and it gets spit out where? To a number line, right? So I just pick a point in 3 space, as long as it's in its domain, pick it out of there, throw it in there. In this specific problem, the only things I can pick come out of a solid ball, radius 3. I pick something out of here, throw it through that function, it'll spit something out. What does that look like? I don't know, you tell me. What does that look like? Okay, don't tell me then. There we go. Yes. So I put in here, do these 12 problems, try the range, okay? Don't get bogged down on range. I would look at Wolfram alpha because you can graph surfaces in Wolfram alpha, all right? You can do it. It's just, it's not the same as necessarily what I'm showing you here. Boy, good thing I passed out the notes for 11.2 because we can actually start 11.2 now. We still have got time. Are we back on track? What were we supposed to finish today? We're supposed to finish 11.2 today. Yeah. Well, at least we're in that section. I'm not trying to rush us, but I really want you to see chapter 13, which is the whole point. We're supposed to finish 11.2 next class. Great. That should work out great. Syntax? Yeah. That's true. That's what I usually do, but there's still things in Mathematica that, I mean, in Wolfram Alpha you can't do as far as when you try and combine things together, or as you're going to see here, watch me do something here. You would never be able to do this in Wolfram Alpha. I'll show you. Okay, remember from Cal 1, does anybody not have the notes for 11.2? Because they're sitting in that filing cabinet over there if you need them. From Cal 1, way back in the day, geometrically, when we took the limit as x approached the number, like in this problem, x approaches 0, we have to look at the limit, what's happening to your function as you come in from both sides, left and right. Are you headed to the same place, right? If you're headed to the same place, we said the limit exists. Did we care about what was happening at the point, though? No. So like in this one, the limit as x approached 0 of sine x over x, the function is approaching what? 1. But when I actually get there, computer freaks out because it's trying to compute sine 0 over 0, undefined. But the limit exists because the limit doesn't care about what's happening at the point. With me? So is 0 in the domain of that function? If sine of x over x is our function, is 0 in the domain? No, but can we talk about approaching 0? Yes, we just have to make sure we approach from both sides. Well, as you might expect, well, I'm not ready for that. Here's another one. Here I'm approaching 0 from both sides, and obviously they aren't going to the same place, right? From the left side, it's approaching, it looks like 1. From the right side, it's approaching, it looks like 0. So the limits do not exist from, the limit from one side exists, the limit from the other side exists, but they aren't the same. In order for the limit to exist at the point, you must be going to the same place. That's just piecewise, but I was trying to just get the jump out of it, just so you see. Anywhere we have a jump, you can't have a limit exist. So this is a key point. The important thing is that in 2D, when you had a graph, if the limit was to exist, you had to be able to approach that point from both sides. Another way to look at it, and I think I will put this, I'll put it here. I have a place to draw right here. I don't know why I always want to go to the board. Look, in this problem, back when we had like y equals f of x, we were going from R1 into R1, right? So our domain was on the real number line. This was our domain. Yes? And let's say we were taking the limit as x approached 0. Then what we would need to do is look in the domain space, which is one-dimensional here, right? And we'd say, I need to approach 0. And the only way to approach 0 on a number line is from the left and from the right. There are only 2 ways to head to 0, right? That's been great for us, but it's going to suck now because, as you're going to see, if you have a function of 2 variables, f of x, y, and you want to know the limit as you approach a certain point in your domain. So now I'm trying to do something like this. Remember, we have the concept of the domain now is in R2, isn't it? And we're going to go somewhere with that and drop that number off on a number line in R. And of course, we put them together, we have our 3-dimensional picture, but this is the domain in what comes out separated. If I want to approach a point, let's say that green point, if I want to approach that point, get closer and closer to it, how can I approach it? Am I stuck with just left and right? I mean, how many ways can, if I say start right here and get to that green point, how many ways can you go there? Infinitely many ways. Right? I can draw a straight line. I can come and do a little curve like that. I can go out here and come back. I mean, there's an infinite number of paths. Some of them are crazy. You go here and go around, come back. There are an infinite number of ways to get to that point. And that is very troublesome for us. Same thing. And there's an infinite number of ways. Oh, no, we're not. But in the real world, what you have to think about is in the real world, you know, functions that are used, like meteorologists use these computers to make these models of what's going to happen. I mean, do you think they go out there and say, hey, look, we're going to come up with a computer program. It's going to predict what's going to happen, but we're going to be able to plug things in like the temperature, barometric pressure, and wind speed. That's it, though. 3 variables, because we're stuck with functions 3. You know what I'm saying? Like, we have functions that take on hundreds of variables and spit out some results based on those variables. So in the real world, our functions are not just R2 to R1 or R3 to R1. We go way past that. But for what we're doing in calculus, we stick to the stuff we can see still, but it all extends out to higher dimensions. I don't know if that addresses your question, but okay. So how many ways can we approach 0? Infinitely many ways. I just did this so I could show you the same thing. I'm trying to get to the origin. How many ways can I go? I can go around here. I can go. And notice that on my surface, what I'm doing is I'm approaching some point, right? Somewhere on the surface, I'm getting closer. Can you all kind of see that red dot over there? No matter how I come in on the domain, I'm getting kind of closer to that red dot over there. And the question is, what am I getting closer to here? Like, what's the z value approaching? What does it look like it's approaching? If I come in there, you see, if I come in closer and closer and closer, looks like it's getting closer and closer to 20, maybe? Let me try this way. Come in this way. Yeah, 20. Yeah, 20 is looking pretty promising, right? Seems like no matter what direction I go in there, it's getting closer to 20, doesn't it? Well, you can't rely on that. The only way to prove that that limit is 20 is to actually be able to come in from every direction, which you can never do. So you might be like, well, how are we going to do this then? Infinite number of ways we can get there. So for the limit to exist at a point A, B, the limit must exist and be the same for every path leading to it. All right, here's our first. This is all we'll do today. We'll do this one example. Let's investigate the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared along several different paths leading to the point 0, 0. So let me just point out the function, right? The surface that's up there that we're going to be looking at is x squared minus y squared over x squared plus y squared. That's what it is. So in there, in case that's kind of slipping your mind, that's actually my f of xy. That's the function. And I'm taking the limit as I try to head towards the origin. You ready to do that? Here we go. So let's see. This is what Mathematica wouldn't be able to do. I mean, Wolfram Alpha. First of all, let me just kind of spin this around so you can see the surface. Do y'all see this surface? I don't know what that looks like. I'm not an origami specialist or anything here. It's kind of weird, though. It has this weird crease to it, right? This weird sort of crease. And then it looks like at the origin, there's something weird happening at the origin. I've got this like cutout space in here. Seems to be something complicated happening at the origin, doesn't there? So the first thing I want to do is, remember, we're trying to approach 0, 0. I want to try and approach 0, 0 along the x-axis. So if I looked at this from the top, here's from the top, just looking straight down. Here's my x value. I want to come in towards the origin. That way, that would be kind of like from the left, right? Left, that's from the left, correct? And then the other side, this would be from the right, correct? But of course, we're not sitting there in 2D. We're up here like this. So it's a little more. I have to kind of spin this to make it look like that. So what I've done here is the black dot is actually riding along the surface. Okay, as I move it, it's actually going to do whatever the surface is doing. If it goes up and down, the black dot will go up and down. The green dot, do you see the green dot there? That's riding along the x-axis. So as I change the value of x, this dot follows that green one around. And what does it look like is happening as I move that around? The black dot seems to be staying the same the whole time, doesn't it? And then over here, still seems to be staying the same. And it looks like it's always, the same height, yeah? Now, how do we show that algebraically? So let me try and show that to you, that this is going to give us the same answer. So I'm going to do this to the side here. We're coming along the y-axis, right? X-axis. The x-axis means that all your points look like what? If you're on the x-axis, your y is 0, right? So you look like this, don't you? Every point along the x-axis has an x-coordinate, and then the y is a 0. So what happens is that I can rewrite this limit. I'm letting my point xy approach 0, 0. But since I'm on the x-axis, all my y's are zeros. So replace every y in the function with 0. And what do you get? X squared minus 0 over x squared plus 0, which is just x squared over x squared, which is 1. And you never have to take a limit because the x squareds simplify to become a 1. Do y'all see that? So if I'm coming along the x-axis, that means y is 0. I should always be 1. Now what's happening at 0, 0 though? At the origin, what's happening? It's undefined, right? It's undefined. You get 0 over 0, that's undefined. So I know that I'm undefined at 0. Now, so does that mean that the limit is 1? I got to go from every possible path, right? Which I already said we don't have time to do that, so why in the hell are we doing this? Well, because it's easy to show a limit does not exist by just showing that coming from 2 different paths, you get 2 different answers. So now come in along the x-axis instead. Y-axis, sorry. Let me back this up Let me take a picture of this. My battery's dead on this. Y'all do it. What are you getting? If you come in along the y-axis, that means you replace all your x's with zeros. What do you get? -1. Right? You get negative y squared over y squared. Y'all see that or not? Do I need to write it? So I get -1, which follows here. Now I have the picture here again. This one you can kind of see, you can see the green is the y-axis. Ooh, it's hiding. There it is. And the black dot's down there on the bottom. No matter what, the black dot's staying down there, -1 the whole time. Can you see the x-axis one up here? We came across this way a second ago, right? And now we're like on this bottom edge. So if we come in along the y-axis, it wants to be down here -1. We come along the x-axis, it wants to be here at 1. So from two different paths, it's going two different places. Therefore, this limit does not exist. That's our conclusion. Does not exist, DNE, since we got different results along different paths. We will be able to say it does exist, but we'll have to use a squeeze theorem to do it. That's the only real way to get it. You will never be able to test every path because it's impossible. It doesn't, no. Here's another one. Now, I'm almost out of time, but I want you to see the picture of this one. So again, this is almost like that weird shape we just had. What I'm going to do is along the x-axis, do you see my dot? See my dot down there? The x-axis right there? Watch what happens as I move along the x-axis. The dot always stays the same. It's actually at 0, right? It doesn't go up or down. With me? If I come in along the y-axis, it actually stays down there also. So it just kind of moves. So from x-axis, y-axis, it's 0. You're all excited. And then you try something different. Like you come in across the diagonal. So instead of coming in along the x-axis or y-axis, you come in along the line y equals x. And if I come in along y equals x, I come in across that top edge. Do you see that? And now I'm up. I'm not down at 0 anymore. I'm up there at 0.5. And so the limit won't exist. So in the previous two, like in this one, right? The previous one, I came along the x-axis, so I went into the equation and replaced all my y's with 0, right? In the second one, I went in and replaced all the x's with 0 to go along the y-axis. And then in this one, when I went along the diagonal, what do? The diagonal is y equals x, right? So replace all your y's with x's or all your x's with y's, and then look at that and try and take a limit. Well, I'm going to come back to this. I just want you to see this because it's kind of interesting. Here's another one. This one's really cool. This one, we'll do all these by hand next class. This one, it turns out that if you come in, do you see my little black dot there? If you come in, no matter where you come in from, it's 0. Where is it? That's x-axis, y-axis. Oh, here it is. This is the one. So watch what happens here. I've turned this. I'll look at it from the top. What I've done is I've made this program where I can actually come in along the x-axis. Whoa, shit. Slow down. The x-axis, or I can go y-axis, or I can do any line in between. So any y equals mx. I can do any line and approach 0, 0. And when I go back over here, and if you do that on any line and follow it across, follow the point, it'll always be approaching 0, 0. So it looks like from any direction, it's 0, 0, like it's headed to 0, until you decide to come in along this very strange path. The parabola leading to 0, 0, if you come in along that parabola, you're up at 1 instead of down where the rest of the surface is. This is a crazy example, but it's a great example to show you that you can approach from infinitely many lines and be headed towards 0, 0. But if you come in along this one path, you're up instead of down there. So we'll do it all by hand next class, but that's kind of where we're headed with this. Yes. Right here. That one will. You mean that actually the limit exists? Yes, but we'll use the squeeze theorem to get it. All right, everyone. Enjoy your Valentine's Day weekend. Yay.